In this video, I'll go over the operation of a Geiger counter. Let's say you bought a fancy new Geiger counter, or you purchased an old civil defense Geiger counter, like this one. Let's say you were able to figure out how to put batteries in the unit, and you was able to put the detector close by some radioactive object, and it went click, 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 click. Good. That means you are a proud owner of a functional piece of radiation detection equipment. In this video, I'll cover what its functionality actually is, what its reading actually means, and how to use it properly. A primary overview of the Geiger counter. You have the meter that has two scales, millirems per hour and clicks per minute. You have a switch that allows you to select a multiplier for the meter above or turn the device off. And finally, you have a radiation detection probe. The radiation detection probe has a movable window that can be opened to allow detection of beta particles. When closed, the detector is only sensitive to gamma and higher energy particles. The primary radiation detection element in the detection probe is a Geiger tube. That is why the entire instrument is called a Geiger counter. The Geiger tube is a gaseous discharge device. When an incident radiation particle passes through the tube, it produces a gaseous discharge which generates an electrical output pulse. The intensity of the pulse is the same no matter what the energy of the incident particle is. Therefore, it is a non-proportional counter. Because of that fact, it cannot be used to take calibrated measurements of more than one type of radiation. Its calibration only holds true for a narrow band of radiation particle energy. In general, Geiger tubes are calibrated to measure gamma radiation. When measuring gamma radiation from a known source, like cesium, then the intensity of the radiation field will correspond to the radiation level indicated by the top scale. When the window is open, where the tube is now sensitive to beta particles, then the calibration at the top of the meter is no longer applicable. Any measurements you take with the window open is inherently uncalibrated. Under that condition, any measurements taken are strictly raw and not quantitative. That figure in counts per minute cannot be extrapolated in any way into a specific calibrated radiation intensity reading. The beta sensitivity of the meter is strictly a utility feature to determine the presence of surface contamination, a strict yes or no, go or no-go determination. That is a result of the fact that you cannot determine the spectral density of the radiation field in question with a Geiger counter. Therefore, you cannot make any determination of the type of the radiation source. Therefore, there is absolutely zero way for you to extrapolate the CPM reading into a calibrated radiation field measurement. When looking for elevated radiation levels caused by man-made radioactive sources and taking calibrated measurements, you should always leave the beta window closed. There is another reason to leave the beta window closed in North America. That reason is to avoid false positives caused by natural radiation sources. It stems from the fact that North America is basically the Saudi Arabia of uranium. If you live in North America, you cannot find a shovel full of dirt that does not contain a few uranium particles. Because of that simple fact, radon is extremely abundant in North America. That is because radon is a decay product of uranium. As the radon seeps out of the cracks in the ground and goes into the atmosphere, it continues its breakdown process. Radon and its decay products generate alpha and beta decay particles. When it rains, the rain has a tendency to scrub those radon decay products out of the atmosphere and concentrate them. If you take a meter that has its beta window open and put it close to a freshly formed puddle of rainwater, there is a high chance that you will detect radiation activity. That radioactivity is a natural radioactive fallout from the decay of uranium under our feet. Usually, man-made radioactive particles and their decay products in the day-to-day environment are the ones that will emit gamma radiation in their natural associated radiation field. When you have the beta window closed, or the meter is strictly sensitive to gamma and higher energy particles, you will have a high level of certainty that any detected radiation field is a result of man-made radioactive elements. When you detect that radiation field, you will also have a degree of confidence that the reading in milligrams per hour is in rough correlation with the actual radiation field intensity. There is a critical distinction with any radiation detector. A radiation detector does not directly tell you the radioactivity of an object. It tells you the intensity of the radiation field in the space in which it currently occupies. The space the detector occupies, not the radioactive item in question. Holding it against a radioactive object does not tell you the radioactivity of that object in X amount. To determine the radioactivity of a specified object, you need to measure the intensity of the radiation field a specified distance from the radioactive object. Once you know the intensity of the radiation field a specified distance from an object, then you can extrapolate as to how much radioactive material would be needed to produce that radiation field at that specified distance. So when you are taking a calibrated reading, you need to hold the detector a known distance from an object, then make a note of the reading. Once you make a note of the reading, take the detector far away from the object and make another measurement. That will tell you the average background radiation for the area, which you can subtract from the first reading to know how much radiation is being caused by that object. When the object is larger or more radioactive, then the distance the reading is taken should be larger to get a more accurate reading. When you log those readings, you should log the measurement taken, its exact distance from the radioactive object, along with the measurement of the level of background radiation a considerable distance from the object. That will allow someone to strictly take your figures and calculate the radioactivity of the object you are cataloging in a quantitative fashion. When you are using the detector with the beta window open to check for surface contamination, you should keep in mind that the radon decay products are short-lived, as opposed to longer-lived decay products from man-made sources. If you pull fresh fruit from the field and detect beta surface radiation on it, do not assume it's contaminated and unusable. Put it in storage for 24 hours and check again. If the radiation level in counts per minute significantly drops from the previous reading, then it's most likely short-lived radon decay products. If the radiation level is close to the reading taken previously, then there's a good chance that the product has been contaminated with decay products from man-made radioactive elements. Normally, for food that is delivered or came from storage, the time in storage is significant enough to allow most radon decay products to fully decay. Remember, after checking surface contamination, or when you are in an area where there may be radioactive elements that can come into contact with the probe to make sure and check to see if there is any evidence of radioactive contamination at the probe. That can be determined by putting the probe in a place you previously took a reading and seeing if the new reading is elevated over the previous one. That will give you an indication to possible contamination of the probe's surface. If that happens, the probe should be fully disassembled and cleaned. Careful attention should be paid to the Geiger tube. It is fragile and can be damaged easily. To help avoid surface contamination of the probe, you can put a thin plastic bag over the probe, which can be discarded after measurements are taken, to protect the probe from long-term contamination. A note that should be made is that a plastic bag will reduce the beta count rate a small amount depending on the thickness of the plastic. If you take a reading with a bag on the detector, then it should only be compared to another reading taken with a similar bag in place. This is the completion of the basic tutorial on Geiger counter use. You should know the basics required to make a useful radiation measurement in the field. Happy radiation hunting. Good day.